rate of convergence for sub-additive ergodic sequences.
Okay, let me thank the organizers for this extremely nice conference. Okay, so my talk today is based on joint work with Michael Demeram and Jack Hansen. They're both from Indiana University. And it's essentially motivated by the following question that is now 50 years old. That was asked by Hammersley and Welsh in 65. And it's also as stated in Kingman's paper in 71. And the question is the following. So suppose XMN is sub-additive ergodic sequence with limit as n goes to infinity of x0n over n given by a constant g. Okay, so that's the time constant. Now the question is the following: what can you say about the rate of convergence of this guy? Okay, so what can you say about this difference, x0n minus ng? So this guy is due to O of n. What else can you say? Okay. I mean, in this generality, the answer is, well, not much, because essentially you can make this rate as fast or as low as you want. Okay. And you see this in a few seconds. So our goal is really just to try to find, so this is the perspective of the talk, is actually to try to find assumptions, actual assumptions on my sequence, so that I actually see something interesting. Okay. And for most of my talk, I'll actually do the following thing. I'll be interested in the following question. I'll do this. I'll just write x0n minus ng as x0n minus its expectation plus its expectation minus ng. Okay. And then I want to understand the order of each of these two terms. Okay. So this guy is random, this guy is deterministic, and I want to understand what is, so this guy, I expected is of order n to the chi. This guy, let's say, should be order of n to the gamma. And I want to ask, what is chi, what is gamma? And is it possible to have a relation between these two? Okay. And again, under just the assumption of the sub-additive ergodic, we are completely hopeless. I mean, you should not expect any relation between chi and gamma. And I'll show you examples. Okay. Okay. So, but let me spoil what is the answer. What we'll do, what we'll show is if my sub-additive ergodic sequence satisfies two properties. First is non-diffusive, and second, if it doesn't have long-range correlations, then in fact, what we'll prove is that actually the dominant term is this guy. Is actually the deterministic sequence. Okay. Okay. So essentially, we just need two things. One is you're non-diffusive. Two, you don't have a long-range no long-range correlations. Then we'll get that actually gamma is actually bigger than chi. Okay, and I'll be precise. Sorry? Sorry?
What is non-diffusive?
Non-diffusive means that this guy is nonlinear. Chi is not equal to a half. I'm just excluding some of IIDs. Okay? And in particular, number 1 and number 2, they expected or they conjectured to hold for many models that includes models in the KPZ universality class, first pass interpolation ZD, longest common subsequence, etc. Okay, good. Okay. So let me give you, let me go slow. Okay, let me just state what a sub-additive ergodic sequence is first, and I'll give you examples. Okay, so here is the definition. We say that XMN is a sub-additive ergodic sequence if it satisfies three things. Number one, it's sub-additive. So X0N is less than or equal to X0M plus XMN. Two, it's stationary on the shift, and the shift is ergodic. So if I look at the distribution of X M plus 1, N plus 1, this guy has the same distribution as X Mn, and the shift is ergodic. And number three, well, the expectation is bounded below. There exists some constant, some positive constant, so this holds. Okay, if I have 1, 2, and 3, then it's a classical theorem of Kingman that this constant g exists. Okay, so actually the limit of x0n over n is equal to g, almost surely now 1. Okay, this guy is a constant. Okay, let me give you examples. Okay, and examples they try to emphasize 1 and 2. Okay, example 1. That's the one that we learned in kindergarten. We just take sum of IIDs. If I take x1, x2, xn IID with finite mean, let's say mean 0, then well, I can just define xmn to be the sum of xm plus 1 plus xn. This is a sub-additive ergodic sequence, right? And in this case, we have chi is equal to a half, because we know the order of the variance of x0n is equal to n. And we have gamma equals negative infinity, right? If I compute the expectation of x0n, that's 0, minus g is 0, I just get, this guy should be over n to the minus infinity. Okay. So I get these two. Okay, and this certainly does not satisfy this. Okay. So this is the first example. Okay, example 2. So essentially this guy justifies why I want to be non-diffusive. Okay. Example 2. Take fractional Brownian motion. With exponent h in 0, 1. Okay, so then, and then I define xmn to be just b, let's say h n minus bhm. Okay, this is again, it's additive. It is fractional Brownian motion is the increments is stationary. So it satisfies 2, and it also satisfies 3. So again, it's a sub-additive ergodic sequence. And if I compute the variance, then the variance of x0n is n to the 2h. Okay, so that tells me that chi in this case is just h. And now I'll do one thing that I could have done there in example 1. I could take this guy and I just add a deterministic sub-additive sequence. So I can just take this guy and just add A and M. Right, this guy is deterministic. With, well, satisfying A n plus M less than or equal to A n plus A m. With, let's say, A n going back to 0. And it's easy to show, I mean, it's really an exercise to show that for this deterministic sequence, I can make this rate here as fast or as slow as I want. Okay? So in fact, this guy can decrease as low as I want. So that means that I can actually, when I compute the mean will be just this guy. So that means that gamma can be any number between -infinity and 1 in this example. So I can choose this such that a n is actually of order n to the gamma for any gamma in -infinity 1. Okay? So this example shows that actually gamma can take any values between -infinity and 1. Okay? So this should be convinced that I can take any chi between 0 and 1, any gamma. So I should not expect any relation between chi and gamma in general. Okay? But fractional variable motion is the classical example where I have long-range correlations. Okay? So essentially what I want to tell you is that you should avoid 1 and 2. Once you avoid 1 and 2, then you're in the business. Okay, so now let me give you the good stuff. Okay, example 3. So that's the model that started everything. That is first pass percolation on ZD. Okay. So example 3. FPP on ZD. Okay. So what is FPP? Well, it is the following. So suppose I give you a collection of weights that are called tau e, index on the edges of ZD, and I'll take them tau e to be non-negative and IIG. Okay. And then the way that you what you do is the following: you take 2 points in ZD, x and y, and a path between these two. So here's a path. So it's a collection of nearest edges. Then given this path gamma, well, we should know this guy. This path sigma, the passage time of sigma is just the sum of the edges in sigma tau e. Okay? So that's the cost to go from x to y using the path sigma. And then the passage time from x to y is just the minimum. Okay? So here's txy is just the minimum over gamma of minimum of sigma t sigma. Okay? So this gives you a metric in ZD, and it satisfies 1, 2, and 3. Okay, so what I'll do, I'll just say that x and n. So let's just look at this guy, x m n, just to be tm e1 and e1. Okay, the passage time between on the axis. So I'm looking at this guy, that's coordinate m. Okay, this is an example of a sub-additive ergodic sequence. And that's the guy that motivated the whole theory. That's the model that was in Hermesel-Wash. Okay. So in this case, what do we know about chi and gamma? Well, maybe I should move this up. Okay, in this case, we have plenty of conjectures. So for instance, d equals 2. We expect that chi and gamma. So for d equals 2, we expect that chi is equal to a third. Gamma should also be equal to a third. For general d, well, as d goes to infinity, it is expected the chi should go to 0, and gamma, well, I don't know. Okay, so that's example 3. Okay, now spend a lot of my time going back to this example. Okay, now let me give you example 4. and that'll help me to make my condition on no long-range correlations precise. Okay. So example 4 is the following. It's also a cute model. It's a cute problem. Suppose that I give you IID random variables. And they take values between 0 and 1. And now you think that xi is just the size of the package I. Okay? And now what I want to do, I want to pack the first n packages. Okay? So I want to ask, I'll define the following random variable. So x0n is, I have boxes of size 1, and I want to pack the first n packages. So you see, the rule is I cannot exceed the size of the package. Okay, so x0n is the number of packages that fit the minimum, that fit x1 up to xn. Okay. So that's known as Bean packing problem. And again, this is a sub-additive ergodic sequence. It satisfies 1, 2, and 3. Because to pack the first n guys, I need less packages than I need to pack the first m and the m to n. Right? It could be that I can actually take one guy and just fit in the box. So it's sub-additive.
Each box has capacity 1 or something?
Each box has capacity 1, and I have these packages which are just the xi's of size xi, and I want to fit in the minimum number of boxes. Okay. Then you can check 1, 2, and 3. Okay. The nice thing about this model is the following property, which is if I look at x0n and xn2n, x2n, 3n, these guys are independent. Okay, this guy only depends on the size of the first n boxes. This is box n plus 1 to 2n, and so on. Okay, that's example 4. I'll give you one more example, and then I'll just start. Okay, example 5. The longest the longest common subsequence. Okay. That is the following. You just take let's say xi and yi are just Bernoulli IID Bernoulli 1/2. They're all independent of each other. What I do, I just write down the sequence xi up to n. Then I write down below the yi's. And I look at the longest common subsequence. So for instance, here I guess it's this. It's 5. Okay. So again, this is another example of sub-additive ergodic sequence. And in this case, actually, there is a conjecture that chi should be little o of, well, chi should be less than or equal to 2/3. Okay. Okay. So these are the examples. Now I want to actually try to explain what are the conditions. Okay. Yeah. Go ahead.
Do you really mean subsequence or subinterval? Because what you underlined was an interval.
I really mean subsequences. Any in that example was just horrible. Yeah, I know. It was everything was attached. Anyways, okay. So now let me start to be precise. Okay. Okay. So what I mean by chi and gamma. Okay. So here are the definitions. First of all, it could be that they do not exist. So I just need to be careful. So I'll define, so here are the definitions. I'll define, so I need to go slow, and I need to define chi upper, which is the lim sup of expectation of x0n. I'll do this. Log expectation x0n minus ng divided by log n. Okay, and chi lower. Gamma, sorry. Lim if of the same thing. Okay, this guy always exists. And same thing for chi. So chi upper is lim sup of variance x0n divided by log n. And chi lower is the lim if of the variance of x0n log n. Okay. Good. So now let me write down what I mean. So this is the definition of the exponents. Okay? And what I'll assume, so here's the assumption. I'll assume that chi exists. So I'll assume that chi upper is actually equal to chi lower. Okay? In other words, if you prove that, for instance, the variance of x0n is bounded by constant n to the 2 chi, or maybe this should be 2 chi, sorry. and I'm missing a log, yes. Thank you. It should be the exponent. Okay? So if you know that the variance of x0n is bounded below and above by a constant n to the 2 chi, that is exactly your exponent. Okay, okay, so the assumption is that this guy exists. Okay, in many models, including first pass speculation, is not known. Okay. Good. Now let me try to explain what should be, maybe I'll just put this guy up. What are the assumptions on long-range correlations? Okay. So what I'll need is actually something that says that I'm weak dependent. One thing is that this suffices. Okay, so that would be my condition 1. Okay, I'll give you 3 conditions. If one of the 3 satisfy, I'm happy. So one is this guy. This is certainly not true in first passage. Okay, if I do first passage, if I just do here is 0, m, and n. Here's the optimal path. Well, they are not independent. But you expect that, their dependence is actually tiny. You only depend in this neighborhood of m. Right? So they're sort of weak dependent. So if m and n are large, this path, they will only intersect in the small region around n. Okay. So now, so what do I need? So now I need to write. So condition 1, if my model satisfies this guy, then I'm happy. Okay. But it's not always true that condition 1 is satisfied. So the condition 2. So condition 2 is, says something about the covariances. Okay. So condition 2 is there exists u 0, 1, 2, to r, such that ur goes to 0, and if I look at the maximum, and I'll explain this in a second, of yi bigger than 0, of the sum of the covariance of x in I plus 1n x jn j plus 1n, and I look at I and j, there are 4 by r, and I divide by the variance of x0n, then this guy is less than or equal to u of r. Okay, and this holds for all n. Okay. So essentially what I'm doing, I'm estimating what is the covariance of of the sequence when I take guys that are I take guys that are far apart by r. Okay, and then when I take r to infinity, then this covariance should go to 0. See? So this is a way to state weak dependence. The important thing is that theorem is that actually can verify. So this is the first step. And Hansen is that actually if you assume, if you do FPP on ZD, and if you assume that expectation of tau e to the d plus epsilon is finite, then C2 holds. Okay. So it's possible to verify this condition. And in fact, it really represents what I said. I want to take two guys that are far apart. The covariance, the correlation should go to 0 on these two.
You know how fast?
I don't care how fast, but it's uniform. And you take this maximum in I and maximum in N. So it's a priori, that's condition 2.
Maximum over I and J.
It's a maximum I and, oh, J is, when I give I, J is defined. Okay. Good. Okay. Then there's a third condition. You can replace C2 by just requiring, if you don't like that guy, here's another condition that is also satisfying FPP. So this is C3. So suppose that you have the following fact. You can compare variances. So if you do variance, there exists constant C1 and C2. Positive such that the variance of, if I sum x I minus 1 n I n, then this guy is actually bounded above by B variance of x0, where B is any set of index of size little b. So I get a bound when I add up these contributions by just one single element. And I also have a lower bound. So variance of x0n is bounded above by variance I equals 1 to b of x I minus 1n no, C2. And maybe I need a beta. Okay, so if I have these two bounds, which certainly is true in this case, because the variance will be additive, and I know how to control the alpha mixing, so I need okay, I want so if the alpha mixing, so if I define if this sequence is alpha mixing with constant bounded by some constant C3 x to the minus k, we're okay, then I'm also good. Okay. Condition 3 is also satisfying FPP. Okay. So I need two bounds for the variance and a condition on the mixing coefficient for my sequence. Okay, now I'm ready to state the main theorem, one of the main theorems.
What is alpha n of x?
Sorry?
What is alpha n of x?
Oh, what is alpha n x? I'll tell you. Alpha n x is just alpha n m is the sup over k non-negative, the sup over a and b of the probability of a intersection b minus probability of a probability of b, where this guy a is the sigma algebra generated by the first any elements of my sequence, b is the sigma algebra of generated by the elements of the last n plus k elements. So I started n plus k to infinity, so they differ by k. Okay. So that is alpha and m. Okay, so sorry.
Between n, m, and
N and m. Sorry. Sorry.
I'm confused between n, m, k, and x.
Oh, okay. Very nice. So A. So let me write. A belongs to the sigma algebra generated by x I n, where 0 is less than or equal to I, less than or equal to k. B generated by the sigma algebra where I shift by m. So the sigma algebra generated by x I n, where 0 or I is bigger than k plus m. Okay, so I shift my sequence by m. I look how independent they are. Okay, so I take one event that depends only on the first m guys. On the first k guys, I shift by k, by m, sorry. I look at another event in that sequence. I want to estimate this guy. How is it decay? Okay.
The bound on the right is
The bound on the right.
the minus
This
k
should
for
be
all k.
yes, for all k. So it should be smaller than any polynomial.
Where is k on the left?
I think
Oh.
a different size.
That's just a horrible notation over. I mean, this should be like theta, and this is theta. Okay. I was trying to avoid defining alpha, but
Where is theta on the left?
theta is any positive number.
So any
So this guy should be it should be smaller than any polynomial. It should decay to 0 exponentially fast, for instance. And x is 0. Okay. Anyway, so now I'm ready to state the theorem. Okay, so here's the theorem. Again, myself, Michael, and Jack. Maybe I should erase this guy. Which is exactly what I said. If I okay, theorem. Assume chi upper equals chi lower, and that either C1 or C2 or C3 hold. Okay. Then the following holds if chi is not a half, then gamma lower is actually bigger than chi. If it turns out that chi is a half, but I know that the variance of x0n is big O of n log n to the beta, then we can prove that actually gamma upper is bounded below by chi minus 1/2 2 to the beta minus 1 minus 1. Okay, so that's the theorem. Okay, remarks. If I take beta to infinity, this guy actually goes to 0. So I actually recover this guy. And again, I rephrase this guy. This assumption here is not known in FPP. Okay. Okay, so that's the main theorem.
Second is known for some distribution.
Well, yes, but in the second guy, well, maybe I should have said this. Suppose that this guy holds and chi is equal to a half. Okay, so chi is a half, but the variance, I'm avoiding being sum of IIDs. Okay, then I get that guy. We should just write that. Okay, if I apply this to FPP, actually not the theorem, but the way that we proved, I actually get an improvement on the values of gamma. And here's the next thing that I want to state. Okay, so take so theorem, take FPP on ZD. Then the following holds without any assumptions. Then actually gamma lower is at least negative a half. Meaning that if I look at expectation of the passage time from 0n minus ng, well, this guy is at least n to the minus a half. Okay, it sounds a small, at least 1/2. Yeah, minus 1/2 there. No, minus a half. Minus a half. I'm putting this guy is going to 0. This guy is going to 0. Okay, I'm looking at this difference. This difference should be of order n to the gamma. Okay, gamma is less than 1. This is a horrible bound, Ron. Okay, this is a horrible bound. But actually, if you check what is known about gamma, then the best result before this guy was a theorem by Caspin back in 93, where he showed exactly the bound it's less than or equal to n to the minus 1. Okay, so it's a small improvement. It's a small improvement, but it's in n dimension. So for instance, if you take d to infinity, you expect that this guy should be of order constant. This guy should be 0. Okay, I'm not looking at 2 dimensions. Okay. Good.
Number.
New theorem.
It's a new theorem.
Okay, different.
And with no assumptions on the chi. Okay. But again, okay, good. Okay, so let me tell you what is actually known. I'll try to give you a sketchy proof of this guy. But let me tell you what is actually known about the exponent. Okay, I just told you what is known about gamma. In the first pass percolation case. Okay, so on FPP, so previous results, I need to mention one guy, which is the result. It's a beautiful paper of Alexander. So actually, in '97, he proved a version for for sub-additive ergodic sequence on ZD for a large class, including first pass percolation. He proved a version of gamma less than or equal to chi. Okay. But this chi here is stronger than ours. I mean, this is exponential concentration. Okay? So if you knew that you have exponential concentration and the variance of order chi, actually combined with that guy will give you gamma equals chi. Okay, so the non-deterministic part has the same order as the fluctuations, as the random fluctuations. So that's one, and it's a very nice paper. How about chi? What do we know? Well, we know that we know that the variance in FPP. So in FPP, we know that the variance of T0n E1, this guy is bounded by constant n log n. And this is the work of Benjamini, Kawai, and Schramm for the Bernoulli random variables. Then there is Benaim and Rossignol for nearly gamma. And then there is the work of Demram, Hansen, and so, where you just need to assume a finite second moment. Okay, tau e, log tau e, finite. Second log moments. So that's what is known about chi. So essentially we're saying that chi is less than or equal to a half, but it's suddenly. Okay.
Is it known in FPP that kappa bar are equal? No.
No, it's not known. I mean, this is a big assumption. That guy there is a big assumption. Okay. So this is the best thing. So I'm saying here that kappa upper is less than or equal to a half. Okay. How about lower bounds? Well, lower bounds. This is the there's a sequence of papers. There is a paper of Pimento and Perez in the exponential case. Then there is Newman-Pisa. And there is myself and Demram. So Newman-Pisa deals with the case where you don't have a flat edge in the limit shape. This guy deals with the case where you have a flat edge in the limit shape. We can get it, actually the chi lower is at least, well, variance of T0n. Is at least log n. It actually diverges. Okay. But it's still very far away, and this is dimension 2. Okay. This is very far away from the conjecture of chi equals a third. Okay. Good. Okay, let me try to sketch the proof of the theorem. And then you see, in a way that actually you see the assumptions coming in. Okay. Proof. Okay, proof. Let me just do, so the proof goes by contradiction. Okay, so let's assume that actually gamma upper is less than chi, which is less than a half. Okay. So weak dependence, the conditions that I wrote, they have just one purpose, which is just to get you a central limit theorem. Okay. So weak dependence will get you a CLT, not for x0n, but for if I do if I look at the sequence x0n, xn2n, and so on. Okay. So in fact, what we'll prove is we'll prove the following thing: if I do x, if I write x prime to be x minus its expectation, then you can get the following fact. You can get the x0 n prime plus x m n minus 1 mn prime divided by square root of m variance of x0n. This guy converges to a Gaussian. Okay. So that's why I use the weak dependence. Okay, and in the place to get this, there is a paper of Cox and Durrett. And another one, this is 86. And there's a paper of Newman where they handle the two cases, C2 and C3. This is a 92. Okay, so I use weak dependence just to get a CLT if I do sums of these blocks. Okay. Now, that's step 1. Okay, this is step 1. Okay, now let's do step 2.
So this requires chi upper bar equals chi lower bar. This part of the proof.
This part doesn't require. Okay. Well, we require. Yeah, it does not require the chi equals. Okay. Okay. Now step 2. Step 2, I'll just use sub-additivity. Okay. So what I'll do the following thing. I'll just write x0mn prime. This guy is, well, by sub-additivity, this guy is, well, let me just write like this. This guy is bounded by the sum k equals 1 to m x prime k minus 1m kn plus m times expectation of x 0n minus expectation of x 0mn. Okay. I'm just writing this guy is x 0mn minus its expectation. So I use sub-additivity. I get the sum of these terms. And then I'm just writing minus expectation. I'm just adding and subtracting the expectations. So the only thing that I use here was just sub-additivity, property number 1. Okay, but now I know what this guy is. This guy, I know that actually the time constant, G, is actually the infimum in n of expectation x 0n over n. So this guy is actually bigger than G times mn, sorry. So that tells me that this is bounded above by k equals 1 to m, x prime k minus 1n kn, plus, then I can factor m, expectation of x 0n minus ng. Okay, simple inequality, just use the sub-additivity. Okay, so that gives me this upper bound. So how do I get a lower bound for the variance? So what I'll do, remember, I'll prove by contradiction. What I'll do, I'll prove that chi, if this holds, actually chi is less than or equal to a half. And that will be a contradiction. Okay, so this gives me a lower bound for the variance if I do the following thing. So actually this tells me that the variance of x 0mn is bounded below. Well, when this guy is negative, I can reverse the inequality. I square, take expectation. If this guy is negative, I'm in good shape. So this is actually bounded below by expectation of this guy plus m times x0n minus ng square negative part. I have this inequality for these two random variables. If this guy is negative, then I can square and switch, take expectation, I get this. Okay, but now that's pretty good. Because for this guy, I know that I have a CLT by my assumption. This guy should be just order of n to the gamma. So this guy here is of order what? It's of order square root of m variance, square root of the variance of x0n. This guy here is of order m times n to the gamma. So this is actually m to a half times n to the chi plus m n to the gamma. But our assumption is that actually chi is bigger than gamma. So if I take m to be of order n to the epsilon, then actually this guy dominates. So our assumption is that actually chi is bigger than gamma, so I can choose m to be of order n to the epsilon is small, and then I can just erase this part. Of course, there's a lot of garbage going under the carpet, but that's essentially the idea. Okay, but then if this holds, then I have a CLT. And what I get, I'll get the following bound. So then if I normalize, if I divide everything by mn, then I just need to look what is the probability of this guy being negative. But if I normalize this guy goes to a Gaussian. Probability of being negative is bounded uniformly below by half. Okay, can put actually. So actually, what I do is that in the end of the day, what I'll get is this: variance of x 0mn. If I normalize by mn, then I get that this is bounded below by 1/2 variance x0n divided by n. Okay, and that is step 2. And then it turns out that actually this a half here helps you actually to iterate this bound, and then it'll tell you that actually chi must be at least a half. Okay, okay, so that's step 3, which is more technical, but it actually just follows from this inequality. Okay, and that's a contradiction, because we assume that chi is strictly less than a half. Okay, so that is the sketchy sketch of the proof. But essentially, you see what comes in. I need the weak dependent assumption to get a CLT, and then I have to essentially do this bound. Split into blocks. Go ahead, run.
Your assumption was that chi is
different from a half, was it that also chi is less than a half in the theory?
No, good point. I can also have the same proof for chi bigger than a half. Not this proof, but a different proof.
But the same result. Though.
But the same result. Okay? I was very careful. Chi is if chi is bigger than a half, same thing. But it could be that, okay. Anyway, so that is sketch of the proof, and maybe I'll just stop here. Okay, if you have questions, go ahead.
Questions?
Go around.
You had this trick of adding a sub-additive deterministic sequence. That would change the means. So does that say anything about the sign of the difference, the expected x0n minus ng, the sign of that? Because if the sign is negative by adding the sub-additive sequence, maybe you can make it 0?
Well, if you go back to Kingman's proof, original proof of the sub-additive ergodic theorem.
It already says that it's a bond.
No, it doesn't say. It's you can always there's a way to decompose every sub-additive ergodic theorem sequence as something that is non-negative plus something that is actually additive. So you can just use that decomposition. Okay, and then you can work out. Essentially, this theorem is telling us that if you see when I add a deterministic sequence, I can only increase gamma. See, so that doesn't have, I mean, that's exactly what I was saying. I was saying that gamma is at least high. It could be that the fluctuations are just given by your fake deterministic sequence that it's built in. But Kingman's theorem tells you they actually can decompose.
I'm just confused if the theorem should have gamma up at the bar above, because in the proof you seem to be using.
I'm just using this proof. Oh, this is just a sketch, but the proof. The only thing that I use is gamma up.
Gamma low.
Oh, gamma lower. That's bad. That's my.
Gamma low.
Yeah, it should be gamma lower. It's for the chi different than a half. It's the strongest statement. Okay.
So that's for any dimension, the minus 1/2.
And
There's no
dimension.
hope of like improving it with an argument which is dimension
That
dependent.
is dimension dependent.
The weight dependence was if you just assumed that you were going to 0, if you assumed better decay, which
I don't see how to do this. Like on. No, I'd love to. I'd love to give you 2/3. Yeah. Next year, maybe.
Any more questions?
There were a result by Billingsley about the central limit theorem, this last result. You said it's by Newman and Durrett. Didn't Billingsley have a paper as well on central limit theorem? Just using ergodic. I don't think he used this weak dependence, weak dependence result. There's like another condition.
I see. I don't know. I don't know this result of Billingsley. But you see, the only thing that for my assumption of independence is again just to get a CLT. So if you have a different assumption, that'll work too.
So do you see any place where you could include some more assumptions to prove that the limit, the distributional limit, if it exists, will not be normal? Like, I guess first phase of percolation, it's expected.
Well, at some point we'll do that. Go around.
Does this argument give you something about the tails? You have variance. Maybe you can ask about the probability for a deviation.
Yeah, I don't know, Ron. Maybe well, we just look at the variance at this point. But maybe.
Any more questions? Okay, so let's thank both the speakers of the morning session.